This is going to be a super fun video. Gradient, divergence, and curl belong to the world of vector calculus, which is a specialized subfield of multivariable calculus, and in order to understand them, we first need to build a solid foundation with four basic concepts: scalars, vectors, scalar fields, and vector fields. A scalar is simply a number. It has magnitude but no direction. Examples of scalars are temperature, mass, time, or height. For instance, if the temperature at a place is 30 degrees, that number alone fully describes it. There is no direction involved. Then a vector has both magnitude and direction. For example, wind blowing with a speed of 10 units toward the east is a vector. The number 10 tells you how strong it is, and east tells you which way it points. Next, a scalar field is formed when a scalar value is assigned to every point in space. For example, suppose at the point with coordinates 4, 3, the temperature is 217 degrees Celsius, and at the point 8 and 1, the temperature is 83 degrees Celsius. Each point has a single number attached to it. That collection of numbers spread over space is called a scalar field. Then a vector field works the same way, but instead of a single number at each point, we assign a vector at each point. A classic example is wind flow. At every coordinate in space, the wind has a speed and a direction. So at one point, the wind might be blowing slowly toward the northwest, while at another point, it might be blowing faster toward the southwest or northeast. The collection of all these vectors distributed in space forms a vector field. Now, to describe scalar fields mathematically, we use scalar functions. A scalar function takes coordinates as input and outputs a single number. For example, a function might take x and y as input and give you a height value like f of x, y equals x squared plus y squared, which outputs a single number like 13 when x is 3 and y is 2. So, the height at 3, 2 is 13 units. Then, at origin, height is 0. Then, maybe at 1, 3, the height is 10 units. Now, if we want to draw this in 3D, do one thing. At each point in the xy plane, whatever is the value of the height, make a segment of that length rising upward from the plane along the z-axis like this. This way, if you plot it in 3 dimensions with x and y as x and y coordinates and z representing the value of the function, it creates a smooth surface shaped like a giant bowl or pit centered at the origin. Then, to describe vector fields mathematically, we use vector functions. A vector function takes coordinates as input and outputs a vector with components in different directions. For example, v of x, y equals a column vector where the first entry is 2x and the second entry is y. If we evaluate this function at the point 1, 3, the output is a vector telling you to move 2 units to the right and 3 units up. At the point 3, 4, the output is a vector that tells you to move 6 units to the right and 4 units up. This means the further you move away from the origin, the longer and stronger the vectors become, because the magnitude of the output increases with the distance of the coordinates. Now, we introduce a very important object called the del operator. It is written as a downward-pointing triangle and pronounced as del. The del operator is a vector-type operator that performs partial derivatives in different directions. In 2 dimensions, you can think of it as having one component that differentiates with respect to x, and another that differentiates with respect to y. Because it has multiple directional components, it behaves like a vector. To understand what a partial derivative is intuitively, imagine you are standing on a hill where the height depends on both your x and y coordinates. Now, if you want to know how the slope of this hill changes as you walk strictly to the right, in positive x direction, while keeping your y position perfectly constant, That rate of change is the partial derivative with respect to x. Similarly, if you want to know how the slope of this hill changes as you walk strictly to the north, in positive y direction, while keeping your x position perfectly constant, that rate of change is the partial derivative with respect to y. Let us now see what happens when we apply the del operator to a scalar field. This operation is called the gradient. When we take the gradient of a scalar field, the result is always a vector field. This is extremely important. This is because the gradient calculates the partial derivative in each coordinate direction simultaneously. Instead of just giving you a number, the gradient points toward the higher scalar values. To see how this works in practice, let us look at a concrete mathematical example. If we have a scalar function, f of x, y, equals x squared plus y squared. As mentioned earlier, this creates a surface shaped like a giant bowl or a pit centered at the origin. Now, the partial derivative of this function with respect to x is 2x. This is because, while taking a partial derivative with respect to x, we treat y as a constant, and thus its derivative becomes 0. Similarly, the partial derivative of this function with respect to y is 2y. Now, to find the gradient, we apply the del operator, which gives us a vector field of 2x, 2y. Its vector field will look something like this, right? Here comes the satisfying moment. Suppose you place a ball on this surface at the coordinate 1, 2. So x is 1 and y is 2. Put it here, and we get the vector 2, 4 as the gradient. Now note that even though the bowl is three-dimensional, the gradient only lives in the two-dimensional world of x and y. When we find that the gradient at the coordinate 1, 2 is the vector 2, 4, we are looking at a flat map of the bowl from above. This vector 2, 4 does not point up into the air. It points along the flat ground toward the direction where the hill is rising the fastest. So after moving 2 units to the right and 4 units to the north, the next coordinate of the ball is 3, 6. At that point, you will have a height of 45 units. So in 3D, it would look like the ball moved from this point to this point along the surface. Ultimately, if you place a ball on the surface, the gradient tells you which direction you would have to push it to go uphill as fast as possible. Conversely, the ball would naturally roll in the exact opposite direction of the gradient to find the bottom of the pit. Now let us move on to vector fields. When we try to apply the del operator directly to a vector field, we must be careful. Both the del operator and the vector field are vectors. There are only 2 meaningful ways to combine 2 vectors, either the dot product or the cross product. If we use the dot product, we get divergence. If we use the cross product, we get the curl. First, let us talk about divergence. Divergence is defined as the dot product of the del operator with a vector field. The result of divergence is always a scalar field. The word divergence literally means spreading out. To build intuition and understand it mathematically, imagine a vector field V of x, y equals a matrix where the first entry is x and the second entry is y. On a graph, it will look like this. Say this vector field represents the flow of a fluid, such as air or water. At each point, the vector tells you how the fluid is moving. Here is the del operator. Now, take the dot product of these 2 vectors. It will give us divergence of this vector field. We get this plus this. The partial derivative of x with respect to x is 1, and the partial derivative of y with respect to y is also 1. When we add them together, we get a constant divergence of 2. Now, imagine placing a tiny square region in this flow and watching what happens to particles inside that region. If more particles leave the region than enter it, the density or the number of fluid particles packed inside this square region decreases. In this case, Because the vectors point outward and get longer as they move away from the center, more particles leave the region than enter it, and thus the density inside decreases. This means the field is spreading out there, and the divergence is positive. Next, consider a vector field where the first entry is minus x, and the second entry is minus y. Here, the partial derivative of minus x with respect to x is minus 1. And the partial derivative of minus y with respect to y is also minus 1, giving us a divergence of minus 2. In this flow, all the vectors point toward the origin. If more particles enter our tiny square region than leave, the density increases. This means our vector field is converging, and the divergence is negative. Then let us look at a field where the first entry is minus y, and the second entry is x. On a graph, this vector field will look like this. The partial derivative of minus y with respect to x is 0, and the partial derivative of x with respect to y is also 0, so the divergence is exactly 0. In this scenario, the fluid is simply rotating in a circle. If the number of particles entering the region equals the number leaving, the density stays the same, and the divergence is 0. This tells us that even though the fluid is moving, it is not spreading out or packing together. We could have also taken the vector field as constant, like this, representing a steady stream of water flowing uniformly to the right at a constant speed. Every single vector in the entire space is identical in length and direction. Because the fluid is moving at the exact same speed everywhere, the amount of water entering through the left side of the square is identical to the amount of water exiting through the right side. If the number of particles entering equals the number leaving, the density inside the square stays the same, and thus the divergence is 0. Amazing! Now, divergence appears in electromagnetism, where divergence is used in one of Maxwell's equations. A positive electric charge produces an electric field that spreads outward. This corresponds to positive divergence. A negative electric charge produces an electric field that converges inward, corresponding to negative divergence. Now, let us move to our third and final concept, curl. Curl is obtained by taking the cross product of the del operator with a vector field. Unlike divergence, curl produces a vector field as its result. Curl measures rotation rather than spreading. To understand curl intuitively, imagine placing a tiny paddle wheel in a flowing fluid described by this vector field. If the fluid makes the wheel spin, then the curl is non-zero. To find the curl of this vector field, the cross product of this field with the del operator is calculated by finding the determinant of this matrix, where the top row contains the unit vectors I, j, and k. The second row consists of the partial derivative operators with respect to x, y, and z, while the bottom row contains the actual components of our vector field. It turns out to be this. For this specific field, the partial derivative of x with respect to x is 1, and the partial derivative of minus y with respect to y is minus 1. When we subtract minus 1 from 1, we get 1 plus 1, which equals 2. Now, because the curl is 2, the flow will rotate the paddle wheel. The higher the curl value, the faster it will spin, which indicates a much stronger rotational force at that specific point in the field. Conversely, if the curl value were minus 2, the paddle wheel would spin at the same speed, but in the opposite direction. If the wheel does not spin and only moves straight, then the curl is 0. So curl tells us whether the field has a tendency to rotate around a point. Okay, I am super tired right now as editing such videos is really exhausting, but I am doing it just for the love of math. So if you enjoyed this video, please don't forget to like, share, and subscribe to our channel. So good!